Hello, hello. So welcome to our very last unit of the year. We're going to talk about chi-squared test, and then we're also going to talk about a little bit more about linear regression in this unit. So firstly, I just pronounced it. Chi is another Greek letter. It looks kind of like a fancy italics X, and we pronounce it as chi. So it's not chi, it's not chai, it is chi. So again, today's goal is to conduct a hypothesis test for counts of one sample against hypothesized proportions. And we'll talk about what that means. But the whole idea behind chi-squared is that we are comparing counts of data. So it is actually dealing with categorical data, but instead of looking at it as proportions, like we did with a 1-prop and 2-prop z-test, etc., we're looking at counts. So when do we use a chi-squared test? So chi-squared tests are used, like I said, with categorical data. Specifically, we use it when we have more than 2 options for a variable. So instead of just looking at it as did this thing happen or did it not happen, we might have like many different options for a variable, and we're looking at the overall distribution of that variable. Data that you would represent in like a table or maybe a bar graph is usually tested with a chi-square test. So for example, Mars Company claims that M&M's colors follow these percentages. So they say 24% blue, 20% orange, etc. is the percentage of each color of M&M's. I'm trying to figure out where to put myself. But suppose in a random sample of 100 M&Ms, we get these colors. All right, so we have that. What our chi-square test is looking at is the overall proportion or distribution of colors that we got in our sample. Is that drastically different from what M&M said that it was? So just to walk you through this, if I wanted to know, do we have evidence that the proportion of red that's supposed to say M&Ms is different from what Mars claims? If I just was interested in red, so is the M&M red or is it not red? If all I cared about was red, I could just do a 1 proportion z-test. I could find what proportion of red is in my sample and compare that to the null hypothesis that red proportion should be 13%. But if I want to know, is the overall distribution of colors significantly different from what Mars said that it should be, that's when we can do a chi-squared test, because we have all of these options, and a chi-squared test lets us look at that overall distribution for all of the colors, instead of just having to look at one color at a time. So there are actually 3 types of chi-squared tests. We're going to learn the first one today, and then the other 2 types we're going to kind of learn together in the next lesson. So this test we're going to do today is called a chi-squared goodness of fit test, which grammatically sounds weird, but that's what it is. One way that you can tell that you're dealing with a goodness of fit test is that we have one row or column of observed counts. You can think of it as we have really one sample dealing with one variable. So like one sample of an M&Ms, and we're looking at the colors of the M&Ms. The other 2 types are called chi-squared test of homogeneity and chi-squared test of independence. And we'll talk more about those next class when we are dealing more with those. So let's look at an example, and then we'll kind of slowly walk our way through it. So, it doesn't like my image here. So our example says, does the warm, sunny weather in Arizona affect a driver's choice of car color? Perhaps Arizona drivers tend to choose a lighter color with the hope that it will reflect some of the heat from the sun. To see if a distribution of car colors in Oro Valley near Tucson is different from the distribution of colors across the United States, we selected a random sample of 300 cars in Oro Valley. And we have a table that shows the distribution of car color for this sample in Oro Valley, and then also the distribution of car color in the United States as a whole. So here is our given table. Again, that top row is telling us the overall United States proportions of each color of car. And then in the bottom row, we have the number of each color of car in this random sample from Oro Valley. So the question we're asking on this is, based on our data, is there evidence at the 1% level of significance to say that the distribution of car colors in Oro Valley is different from that of the entire United States? So can we say that overall in Oro Valley, the car distribution of colors is different. So the sample, again, we're going back to like the whole point of a hypothesis test. The sample may have slightly different proportions or even what seems like majorly different proportions from the United States. But we're not just looking at the sample. We're trying to find out, is the sample giving us evidence that all of Oro Valley is different? So in other words, what we're looking for is, do our observed counts, meaning the actual sample, match what we would call our expected counts? Is there a difference between what we observed and what we would expect of those numbers if the US proportions were true? Okay, so, and is there a difference, or if there's a difference, could it have just been by chance, or are the differences so large that it makes us doubt those given proportions? So the first thing I would do always for a chi-squared goodness of fit test, or any chi-square test, is find the expected counts. So what this means is I'm looking at my numbers of cars. I have a sample of 300, and I'm trying to decide how many of each color would I expect in a sample of 300 if those proportions for the US were true. So really what I'm doing is just some simple math where I'm going to do, okay, I have 300 cars in my sample. I'm going to move myself so you can see my calculator. So I have 300 cars in my sample, and let's find out what is 23% or 0.23 of 300. So I'm going to do 300 times 0.23, which gives me 69. So that means if these proportions were true, we would expect that our sample would have 69 white cars. And then the same thing continuing. So for black cars, the proportion for the United States was 0.18. So if that proportion was true, I would expect that my sample would have 300 times 0.18 or 54 black cars. And I'm just going to keep multiplying. 0.31 times 300 is 93. 0.1 or 0.10 times 300 is 30. 0.09 times 300 is 27, and then 27 again. And all of those numbers should add up to 300 because that's the whole point. We're saying in our given sample, how many of each color would we expect there to be if those proportions were true? So as you can see, there are some differences, right? We had more white cars than we would have expected. We had less black cars than we would have expected, etc. So these are off in different ways on all of them. But again, our question is not just are they different, but are they different enough that we're now going to doubt those given proportions are true for Oro Valley? Right? So let's start with our hypothesis statement. So we are doing our hypothesis test. So chi-squared goodness of fit hypothesis test is what we are doing. The null hypothesis is basically just that there's no difference, right? Just like always, the null is saying that there's no difference, that everything's the same, nothing changed, etc. With a chi-square test, we don't really have like a parameter to define because again, there's like many different categories of that one variable. So instead of defining a parameter and then writing hypothesis statements, it really is the best to just write our hypothesis statements in words. So I would say something like the proportions for my null hypothesis, the proportions of car colors in Oro Valley are the same as the US proportions. So they're the same as what we would have expected based on the given information. Then our alternate, as you can probably guess, is basically that they're different, that the proportions of car colors in Oro Valley are not the same as the US proportions. So there is a difference, and we only do like difference or not in chi-squared because we're talking about a bunch of different categories. There's never going to be a less than or greater than, because if you go back to our table, right? I went the wrong way. If we go back to our table, right? Some of them were less and some of them were more. So we're just saying, is it overall different? So those are our hypothesis statements. Okay. So chi-square distribution is defined by its degrees of freedom. So we still have a degrees of freedom, and I'll show you that when we look at our chi-squared table in a minute. But for a goodness of fit test, the degrees of freedom is defined as k minus 1, where k is the number of categories. So in this one, just how many different car color categories did we have? That is k, and then minus 1. So a couple other things about a hypothesis test for chi-squared. Is there a confidence interval? No, there is no confidence interval because, again, we have many different categories, and there's not really a good way to estimate what is true for each of those categories all in one confidence interval. So we do not have a confidence interval. We do, however, have conditions. However, you'll probably like the conditions a little bit better with a chi-squared. It's way less work. So our conditions for a chi-squared test for goodness of fit. Firstly, do we have counts of data? We want to make sure we're dealing with numbers of data as opposed to means or proportions or median or standard deviations or anything else. We should be dealing with counts. It shouldn't be weights of items. We have to be dealing with numbers or counts of items. Second condition, do we have a random or representative sample, same as always, from a certain population? And then our last condition, and this is where we used to check for normality. We're not necessarily checking for normality here because it's not a normal model that we're using. It's a chi-squared distribution that we're using. So we're checking for chi-squaredness. Anyway, so our way of checking if our sample size is big enough to make the chi-squared model work, we just need each expected count to be at least 5. So when we looked back at our table earlier where we had all the information, we want these expected counts right here, each of these to be at least 5. So it does pass here for this example. Okay, so those are our conditions for a chi-square test. It's a little bit less stuff that we have to deal with. And then we move into calculations. So same general steps as any hypothesis test. We did hypothesis statements, we check conditions. The next step is we do our calculations. So this right here is the chi-squared statistic. It's the number that we use to find out where we are on the distribution and then to find a p-value. So what this says is this is the summation. So we're going to do this for all individual cells or categories. For each category, we do the observed value minus the expected value. We square that difference and then divide by the expected value. So observed minus expected squared divided by expected. We do that for each category and then we add them all together, and that is our chi-squared value. So if I go back again to my table, let me go back to this, right? The way that I would calculate my chi-squared statistic, if I were going to do this by hand, is I would do parentheses. I'm going to start with my white car category. I'm going to do observed, which was 84. That's what actually happened in the sample, minus expected, 69. I'm going to square that difference, and then I'm going to divide by expected. Right? And then I'm going to add, I don't know why I pushed enter, but I just felt like it. So I'm going to add the second one and do the same thing for black. So 38 minus expected is 54, squared divided by expected. Right? Notice that I'm staying positive. So even though that difference was negative, because I squared it, that made it positive. And then dividing by 54 kind of brings it back down to where we're not dealing with huge numbers. So if I were to keep adding those up together, that would give me my chi-squared statistic. So one way that you can do this, it's a little bit faster, it's kind of just using your calculator as a like repeat math thing. I don't know the word I'm trying to say. And we're going to need to do this anyway later to do the test. So it's good to do it now. If I go ahead and type in all of my observed values in L1 and then my expected values in L2, there is a way to get my calculator to get that done faster. So I'm going to type all those in and then I will come back and explain. Okay, so once I have those in my calculator in L1 and L2, one way that I can use to get the chi-squared statistic a little bit faster, yes, there is a little bit of a quicker way, but I will say if you have an older calculator, I always say this, there's always something, right? If you have a TI-83, or maybe even a TI-83 Plus, if you don't have an 84, you will actually have to do it this way all the time. Otherwise, if you have an 84 or newer, there is a faster way to get to the chi-squared value. but this is a good little trick to know regardless. So I'm basically going to use the list to do that repetitive math faster. So I have my observed in L1, I have my expected in L2. So I went over to L3 and I went and scrolled up to where I'm highlighting the L3. And now I'm basically going to write in a formula using the two other lists. So I'm going to do parentheses. I'm going to do observed, because that's my formula, observed, which is in L1, so second 1, minus expected, which is in L2, so second 2. I'm going to close parentheses and square that, and then I divide by expected, which is in L2. And voila, when I push enter, what it does is it takes each of those information and it does it faster. So it's done all that like kind of repetitive math really quickly for us. So then the last step would be to add all those numbers together, which you can do by hand, but we also have a way of adding those together quickly. So I'm going to go second quit back to my home screen, and I'm going to do second stat math, and then there is a sum option, and then I'm going to do sum up or add up L3. And then that right there is my chi-squared statistic. So 23.2 would be what I get if I did each of those pieces and added them all together like I did. So again, if you do have an 83 or older, whatever, you will actually have to do it this way every time, and I'll explain why in a little bit. If you have a newer one, there is a faster way on our calculator. So let's go back and talk about what that chi-squared value is telling us. Yes, our calculator has an option, but it is a good idea to be a little bit more familiar with our chi-squared table and how that it works. So what does that tell me? How do I know, based on that number, which ours was 23.2, whether to reject or fail to reject our null? So the chi-squared distribution looks like this. It's skewed right. It's got really, really big parts at the beginning, and then as our chi-squared gets bigger and bigger, the probability goes down, down, down. So this is a chi-squared model. Basically, this is x-axis is your chi-squared value, and then the y-axis is like the probability of that chi-squared value happening by chance. So notice that as chi-squared gets bigger, probability goes down, like I said. So this is kind of showing us what chi-squared means. So chi-squared value is basically measuring the distance overall between observed and expected. So the more space there is, the more different observed and expected values are, the bigger chi-squared will be. So a large chi-squared value would mean that overall the differences between observed and expected are very large, which would give us evidence for a difference between the sample or the population that we're looking at and like the expected values that we're given. So in that case, we would reject the null, that they're the same, and say we have evidence that there's a difference. A small chi-squared value would basically mean there's probably not that much evidence of a difference because those overall observed and expecteds were not very far apart from each other. So we would lack evidence of a difference between observed and expected. But how large is large and how small is small? Well, that depends on degrees of freedom, which is based on the number of categories. The more categories you have, right, then the bigger the overall difference is because you're literally just adding them together. So if you have more categories, we expect to get a bigger number for chi-squared because we have more categories. So what we call large and what we call small really depends on how many categories we have. So just to give you a quick look at our chi-squared table, which I will make sure is attached in the resources and whatever in Schoology. But basically, this is the chi-squared table. So what we would do for our problem, we had, I already forgot how many categories we had. Let's go look at it. 1, 2, 3, 4, 5, 6. So we have 6 categories, and remember, degrees of freedom is k minus 1. So categories minus 1. So we had 6 different colors. So our degrees of freedom would be 5. Okay, so we would look on the degrees of freedom 5 row, and we would look for where our chi-squared value would fit. We got a chi-squared of like 23.2. So this is telling us like what is the probability of getting a difference as big as we got. So our chi-squared value, you'll notice, is beyond the last number on this row for degrees of freedom 5. So each number gives us a probability at top, just like with the t-table. If I got like a chi-squared value of 10, 10 is between these two numbers, so that would tell me that the probability of that happening just by chance is between 0.05 and 0.10, right? But because our chi-squared value is beyond the 22.11, that's the last number in the list, that tells me that my p-value, my probability, would be less than the smallest number on the list. So I would need a p-value of less than 0.0005, which is very, very, very small, which would tell us this is a really big difference. But notice is that as we go down the table in degrees of freedom, the numbers in this table get bigger and bigger and bigger, because again, if there's more categories, we expect the differences to be bigger, or the chi-squared value to be bigger, because we're adding together more numbers. Right, notice that 11 is considered, like that's a 0.025 probability. That's pretty significant for a degrees of freedom 4, but 11 for degrees of freedom 9 has a probability of 0.25. So like that's not that unlikely. So what's significant for a smaller number of categories is not necessarily the same. So that's why we use the table, and that's why we use degrees of freedom, because there are differences. So let's go through our car color problem just from start to finish. I will also show you calculator stuff, the super, super shortcut in a second. So we would start with hypothesis statements, which we said already, right? The NOLAs of the proportions of car colors in Oro Valley are the same as the US proportions. The alternate is that they are not the same. Conditions. We were given a random sample of cars from Oro Valley. I forgot to put this, but we are dealing with numbers or counts of cars of each color. And then all expected car counts were greater than or equal to 5. Then we would do our math. Now, just like always, in any other test or interval that we've done, it is okay to skip writing the formula, which you will appreciate on this one because it would be a lot of writing, because you would literally have to write that formula out for each car color category. So we don't have to write the formula for chi-squared, but we do need to make sure and write the name of the test. So I would write chi-squared goodness of fit test somewhere on my paper. Now is where I'm going to show you shortcut. So your first step on calculator would be to go to stat edit and put your observed in L1, your expected in L2. You do not have to do this third step if you have a TI 84 or newer. There is a shortcut. If you have an older calculator, you'll have to do what I showed you before to kind of get to the chi-squared value a little bit quicker rather than having to do it by hand. But if you have a newer calculator, there is a way the calculator will calculate that for us. So observed in L1, expected in L2. Okay. I'm going to quit back to the home screen. I'm going to clear. I'm going to go to stat tests. And then I like to scroll up because the chi-squared options are on the very, very bottom. There is chi-squared test and there's chi-squared GOF test. So we right now are doing a goodness of fit test, GOF, goodness of fit. So this is where if you have an older calculator, that option won't be there. There will only be chi-squared test, and that one will not work for this type of problem. The regular chi-squared test only works for the other two type that we're going to learn about in the next lesson. But if you have the newer calculator, we're going to do GOF tests. You tell it your observed values are in L1, your expected values are in L2. You have to type in the degrees of freedom. The calculator will not figure that out on its own. So I had 6 categories. Degrees of freedom is 5. And then I calculate. And notice that it gives me the chi-squared value of 23.2 that I calculated a minute ago, but it also gives me a p-value, right? If you remember from our table when I showed you, we estimated or figured out that the p-value had to be smaller than 0.0005 because it was on the other side of that biggest number on the chi-squared row. But this is telling us more exactly. It's 3.08 times 10 to the negative fourth, which would be 0.00030877, etc. So it's very, very small. It also gives us, if you're wondering, the CNTRB contribution, I believe that's what that stands for. It's basically giving us like each portion of the chi-squared value for each category. So the first category, the chi-squared was 3.26, and the second category, it was 4.74. You don't necessarily need to know that, but sometimes it's helpful to know like which one of these categories is doing the most damage to the chi-squared value, right? It looks like that second category, that black category, was the most different from what we would have expected. You don't need to write that down. I was just putting that in there. So chi-squared is 23.2. Our p-value is 0.0003. If you're using the table because you have an older calculator, you could just write p-value is less than 0.0005, which is as far as we can go. Degrees of freedom was 5, and then we write a conclusion, like we always have. If p is small, reject the null. If p is greater than alpha, then we fail to reject the null. That's always the same, right? We're still talking about p-value compared to alpha. Our alpha, this was on like 5 slides ago, but the level of significance they told us to use was 1%. So I'm going to say since 0.0003 is less than 0.01, we reject the null, which means we have evidence of our alternate. The proportions of car colors in Oro Valley are not the same as for the US. So that is our conclusion. Right? So I went through a lot of stuff in there today. I'm going to put up one more example. I won't go through this completely, but I just wanted to give you another option for the ways you could be given the expected counts. So this one, it's giving us the expected counts as a ratio. So it's telling us that, we took a sample of 112 flies. The fly types are expected to be in the ratio 7:6 to 3:1. So the way that we would figure out expected counts is I'm going to first add together 7, 6, 3, and 1 to kind of figure out how many total we're dealing with, which is 17. And then basically it goes in order 7 to 6 to 3 to 1. So for that top category, that's the 7. What I'm going to do is say 7 out of 17 times the total number of flies, which is 112. Remember, the whole point of expected count is to figure out how many would we expect to be in that category out of our sample if those ratios were true, right? So always multiply by the total sample size. Don't multiply by that observed number, multiply by the total sample size. So 46.11, which brings me to my second point, which is that if there are decimals in your expected counts or expected numbers, leave the decimals. Don't round them to whole numbers. Yes, I know that doesn't realistically make sense, but if you start rounding, then that's going to majorly throw off your chi-squared value from what it should be. The other hint I will give as you are typing these into your calculator, so if I were to type, here's my observed values, right? Those are pretty easy to type in because they're just whole numbers. One thing that you can do, let me clear this out, is you can do the math to find the expected counts in L2. That way you're not having to do the work twice. You don't have to calculate them and then go type them in. I can just literally say 7 out of 17 times 112. And I push enter and it tells me what it is, and it also puts it in L1 or L2, so I'm not having to do that work later. So then the next one would be, what was it? 6. So 6 out of 17 times 112. The next one was 3. So 3 out of 17 times 112. And then the last one was 1 out of 17 times 112, right? So now I have them in there, and now I'm ready to do my next step in my calculations however I need to. So that is how we deal with a chi-squared problem on the calculator. If you have questions on calculator stuff, especially those of you that have older calculators and you don't get the fancy chi-squared GOF test, make sure you talk to me if you have questions about that. So that is it for today. We will talk in class.